This chart visualizes a terrifying mathematical reality. By 2050, the global population will hit 10 billion. Meanwhile, the amount of arable land and fresh water available to feed them is steadily dropping. Cities are continuously expanding and swallowing fertile soil, while climate change accelerates desertification and droughts, actively squeezing the very physical space we rely on to survive. For thousands of years, our survival depended entirely on physical muscle and the unpredictable mercy of the weather. Replacing the plow with the combustion engine certainly multiplied how much one person could harvest, but it did absolutely nothing to protect those crops from floods, pests, or sudden freezes. The physical limits of soil and muscle have now been reached. To feed the next generation, we must establish an entirely new framework for producing food. In the 1960s, humanity bought itself some time. Scientists like Norman Borlaug engineered high-yield crop varieties that fended off global famine in what became known as the Green Revolution. The core mechanism of this revolution relied on a significant trade-off: massive yields extracted in exchange for massive inputs of synthetic fertilizers and chemical pesticides. Half a century later, the bill has come due. We are looking at severely degraded topsoil, contaminated aquifers, and ecosystems stripped of their biodiversity. This leaves us with a resource paradox. We must multiply our agricultural output again, but this time we have to do it while petting chemical inputs, using less water, and reducing greenhouse gas emissions. Resolving this paradox requires shifting the paradigm away from physical expansion toward the high-precision management of biological systems. Mechanization is often mistaken for high-tech agriculture, but simply adding a GPS to a tractor does not change the underlying logic of the farm. Look at the actual legal definition under Vietnam's 2008 high-tech law. True high-tech agriculture requires deep research and development, integration of modern science, and the creation of vastly superior value. This table maps out the shift in the core variables of production. Notice the most critical factors. The primary driver is no longer the amount of raw acreage or manual labor you possess. The driving forces are now knowledge, algorithms, and data, pushing labor productivity from low to extremely high. And crucially, the vulnerability to weather is eliminated. By moving crops into highly controlled microclimates, product quality becomes standardized and predictable. In this framework, a farm is no longer an open field subject to the elements. It operates like a biological manufacturing plant, where every parameter is programmed and executed with mathematical precision. Look at the Netherlands. Geographically, its landmass is just 1/10 the size of Vietnam, and much of it sits below sea level. Yet, despite this lack of physical space, the Netherlands is the second largest agricultural exporter on the planet. They achieved this through 10,000 hectares of advanced greenhouses. Inside these structures, they use 90% less water than traditional farming and have almost entirely eliminated chemical pesticides. This chart reveals the power of that control. A traditional open field farmer might harvest 3 to 5 kilograms of tomatoes per square meter annually. In a Dutch greenhouse, that same square meter yields 70 to 75 kilograms. We see similar principles applied in even harsher conditions. Over 60% of Israel is the Negev desert, receiving less than 400 millimeters of rain a year. They bypassed this through drip irrigation, delivering precisely measured drops of water and nutrients directly to the root zone of each plant, instead of flooding fields. Today, they layer artificial intelligence and autonomous drones over those drip systems, analyzing real-time field data to maximize yield from the scarcest resources on Earth. Both nations demonstrate how technology allows production to scale independently of local environmental and geographical constraints. High-tech agriculture operates as an integrated matrix, layering several modern sciences into a single ecosystem. It begins at the biological baseline. Gene editing tools like CRISPR-Cas9 allow scientists to program crops at the DNA level, creating varieties that naturally resist disease, tolerate high salinity, and survive droughts. Above the seed is the physical layer. Autonomous tractors and robotic arms handle the intense physical labor of seeding, pruning, and harvesting without fatigue or error. Next is the spatial layer, precision agriculture. Drones map the canopy, identifying exactly which plants need attention, ensuring that water and treatments are applied exclusively where needed. Tying this hardware together is the cognitive layer, the Internet of Things and AI. Thousands of ground sensors stream big data to servers, where algorithms predict pest outbreaks and automatically adjust irrigation valves. Finally, the trust layer. Blockchain technology encrypts the supply chain, allowing a consumer to verify the exact origin, chemical history, and transit path of their food. Managing a modern farm requires the precision of a systems engineer, bridging the gap between agronomy and digital architecture. Geographically, Vietnam holds significant advantages. Its 15 degrees of latitude encompass ecosystems from the rice bowls of the Mekong Delta to the coffee lands of the Central Highlands, supported by expanding internet infrastructure. We are already seeing the early stages of this transition in places like the high-tech zones of Dalat and Ho Chi Minh City, or the sophisticated hydroponic networks built by domestic corporations. But there is a massive structural bottleneck. The average Vietnamese farming household operates on roughly half a hectare to 1 hectare of land. Production is highly fragmented across millions of tiny, disconnected plots. This extreme fragmentation limits economies of scale. From a purely economic standpoint, a standalone farmer cannot afford to install a 20 billion dong climate control system for such a small area of land. Compounding the land issue is the human element. The rural workforce is aging rapidly, and there is a shortage of technicians trained to operate these complex, data-driven systems. Solving Vietnam's agricultural challenge requires addressing the structural organization of land and the technical training of its people, rather than simply importing hardware. Those exact structural and human resource bottlenecks are why a discipline of agricultural technology exists today. The modern farmer has evolved into a data specialist, using biological insights and robotics to manage complex, optimized production cycles. With 10 billion people arriving by 2050, agricultural efficiency has become a critical pillar of global stability. The blueprints for Agriculture 4.0 are already drawn. The task for the next generation of engineers is to adapt these systems and execute them on Vietnamese soil.